right, so now we want to talk about the Doppler effect. But before I do it, you need to watch a video. So I want you to go on the internet and find the Doppler effect. What does motion do to waves? So find that on YouTube, and it will have Sheldon from the Big Bang Theory. So watch it. Okay, now, did you notice that Sheldon was wearing a shirt that had stripes on it? And did you notice that the stripe in the middle was the thinnest, and then on either side of it the stripe got thicker, and then over here the stripe got even more thicker, and then it did the same thing over here. So this is the shirt that Sheldon was wearing when he was describing what the Doppler effect was. Okay, he was dressed as the Doppler effect. So this was an episode of the Big Bang Theory, their Halloween episode, and he was dressed as the Doppler effect. It didn't show the back of his shirt, but the back of his shirt would have had very big stripes. So let's see if we can understand why did it look like that. So let's pretend that you have a source of a wave. So it could be like an alarm clock, and it's located right there. And so it would send out sound waves in all directions like this. All right, now this represents a crest right there. So that would be where the sound waves are concentrated. And then this would be another crest over here, and then this would be another crest over here. What would it be in between the crests? It would be a trough. So you'd have a crest and then a trough in between. You'd have a crest where the line is at, and then you'd have a trough in between. So what would be the distance between one of these circles and the next circle? What would that be called? So that would be the wavelength. So like, for example, the distance from here to here would be one wavelength. The distance from here to here would be another wavelength. Okay, now this is important because he was talking about what does it do to the frequency. So now let's pretend that the source of the sound wave is moving in this direction. So if the sound wave's moving in this direction, then what's going to happen is you still have these circles, but the circles are going to be scrunched up in the front, and then they're going to be pulled out in the back. And then you'd have another circle that's scrunched up in the front, and then it's more spread out in the back. So what happened to the wavelength if it's moving in this direction? So if you're over here, okay, and you are watching as this source of sound is coming towards you, the wavelength is going to get smaller. You see it's getting scrunched up? So the wavelength is going to be smaller if it's moving towards you. Who cares? All right, now let's go back up to here. The speed of any wave is its wavelength times its frequency. So if the wavelength gets smaller, what does the frequency have to do in order to compensate? It has to get bigger. So that was the reason why it says, he said, that as a wave is moving towards you, the frequency goes up. So the frequency is going to be bigger. So if this is the frequency before, this is the frequency after. As a wave is moving towards you, the frequency is going to get larger. So what does that sound like? Okay, so the pitch is going to go up, a higher pitch. Okay, what does it mean for light? Now light is going to be Roy G. Biv. And now I'm going to write it backwards. I'm going to say Roy and then G, and then BIV. So there's a method to this madness, because do you remember that the radio waves were over here and then infrared? So now red is next to infrared. And violet, what's on the other side of violet? Ultraviolet. So if the wavelength is getting smaller, which direction are we going? All right, remember that this side over here had the small frequencies, and then this side over here had the large frequencies. So that as the wavelength is getting smaller, the frequency is going up. So if it normally is, let's say, the color yellow, it's going to turn bluer. So we're going to say that it's going to be blue shifted. The frequency is going to go up. It's going to go in that direction. So if something normally has the color yellow, it's going to become more blue. So we say that the light is blue shifted. Now what about if it's moving away from you? Okay, now the wavelength is getting larger, so that must mean that the frequency is getting smaller. So if something is moving away from you and it's a light wave, so again, let's say it normally was the color yellow, and the frequency is getting smaller, it's now going to be red shifted. It's moving in that direction, so it's going to be red shifted. So you do need to know what the words blue shifted and red shifted mean, and how is that related to what is the wave doing. Okay, got it? All right, one last topic, and then we'll be finished with this lesson. We want to know what would happen if the source of the wave is moving equal to or faster than what the wave can travel. Okay, so we know that the speed of sound is something like 340 meters per second. What would it look like if the source of the sound, so this is the alarm clock that is producing the sound, what would happen if it was moving at 340 meters per second in this direction? Well, now what's going to happen is that these lines here are going to be on top of each other. And so that's that first picture over there on the left. So the lines are superimposing, and remember that each of these waves has energy. And so this is going to make a sound barrier. And it's going to be, and at first it was very difficult for airplanes to go faster than the speed of sound, because they had to break the sound barrier, and they had to get through all of those waves that were in front of them. And so this is going to make a sonic boom when this happens. Now what happens if you go faster than the speed of sound? So then that is going to be the picture that's right next to it, and you notice that it creates a V-shaped thing, which is going to be a shock wave, which is going to travel along the surface of the Earth. And so if you happen to be here, okay, and then the airplane is going in this direction, you don't notice anything until that shock wave passes over you. And when that shock wave passes over you, all of a sudden you hear thunder. And so I could remember being out in the middle of New Mexico and doing geological field work, and it would be a clear blue sky and not a cloud in the sky, and then all of a sudden you would hear the sound of thunder. And only then, when you would look up, would you hear the sound of the jet engine up there. So you had to wait for that sonic boom to go by, and then you could hear the sound of the jet that was way, way up there. So it was traveling faster than the speed of sound. Okay, so for purposes of the exam, can you explain what causes a sonic boom? Okay? All right, so let's take a break. And when we come back, we will take our lesson quiz.